Yeah. Okay, so continuing our lesson here on regression, there are several things that you need to think about that are characteristics of regression. So one is that you're predicting y based on x. This means that you have to be careful about what is your explanatory variable and what is your response variable. So here we have height and seeds, and if I flip, so here's my x-axis and y-axis, and I get some relationship here and I get some line. If I flip this relationship, this line will change. So I'll get a different result. I'll get a different line if I put number of seeds on the x-axis and height on the y-axis. So you can't, unlike correlation, you can flip x to y. It doesn't matter, you get the same relationship. That's not the case in regression. The other thing that you need to think about is how you can make inferences about your results. So how can you extrapolate from your results? So if you have this line based on your data, right? This line keeps going to 0 all the way up to infinity, theoretically. But of course, your data don't go to infinity, and you can't extrapolate to a height of infinity, right? You've measured plants from 10 centimeters to 25 centimeters, and that means that this relationship holds for plants of this height. But it may not hold for plants that are smaller than 10 centimeters, and it may not hold for plants that are larger than 25 centimeters. So if you have a plant that's 5 centimeters, that means that 1 centimeter of growth may not predict 3 more seeds. Just like if you have a plant that's 30 centimeters, 1 centimeter of growth may not predict 3 more seeds. It might predict some other number of seeds. The second is that the relationship may not hold in other areas or at other times of year when you measured. So if you measured this in August, these data may not hold in June. Or if you measured this in 2012, it may be different in 2013. And if you measure these only at Ixnart, right, if you go to northern Mongolia and measure the same relationship in the same species of plant, it may change. So you need to be careful about how you extrapolate, because there are factors embedded in these data that don't show up in the graph, like what time of year you collected the data, where you collected the data. And so if you're going to make inferences beyond your exact data, you have to be very careful about that. The second thing is that these are sensitive to units. Sensitive to units. So this is unlike correlation. So in correlation, what units you have, it doesn't matter. In regression, it matters. Because if you think about what the slope means a change of 1 unit in x changes some units of y. So if I have height in centimeters, and if I have a slope of 3, like we said, so 1 centimeter of growth means, on average, you predict 3 more seeds. If I change the units to millimeters, right, a change in 1 millimeter of growth does not predict 3 seeds. It only predicts 0.3 seeds. But that changes your line, right? If you have millimeters here instead of centimeters, your line would change. And that would change your slope, that would change your intercept. It's a fundamentally different line. Right? Your correlation coefficient, 0.97, would stay the same, but your regression line would change. So if you've done a regression in a certain set of units, so certain units in x and certain units y, you have to stay with those units, and if you want to change them, you have to redo your whole regression. So you have to, once you set units for x and set units for y, you have to stick with them or change it. So the last thing, and probably the most important, is to discuss r squared. So r squared. You see this a lot, and it's a measure of how successful your regression was. And what it measures is really the variation in y that's explained by regressing y on x. So what that, in this example, means is that if I measure seeds, and there's a lot of variation in number of seeds, but if I just regress number of seeds on height, then I know in this case, so r here is 0.97, so an r squared with 0.97 squared is probably 0.95, so that means that by regressing number of seeds on height, I've explained 95% of the variation. in the number of seeds based on just knowing the height of the plant. So this is, for this, that's quite a lot, right? We know if you have 95% of the variation explained, that means there's only 5% remaining that we don't know, or we can't explain with this model. But that's a very successful model. So you see this number a lot. It's of course related to regression. You report this with a regression, but it comes from correlation, right? It's just this correlation coefficient squared, and so that emphasizes that correlation and regression are different, but they're very similar. They're fundamentally linked, even though they're different measurements. So with that, I think we're going to end. One thing I'll note is that I've been talking about single regression. So I've been saying number of seeds here. So y is predicted by x, only one x. What we'll eventually get to is a multiple regression, where y, a response variable, can be predicted by many explanatory variables. Right? So I have some intercept still, and then it would be like this. It would be B1, x1, B2, x2, and maybe I have however many x's you want. Well, how many x's you have is limited by your sample size, but we'll talk to that. But essentially what this means, so for this example, if I wanted to predict the number of seeds, I would have maybe height as one variable. That would be my x1, and then x2, maybe I had precipitation this year, and then x3 might be soil type, so what kind of soil there is. So it can be, these explanatory variables can be a lot of different things. But this is a multiple regression. What we've talked about here is a single regression. We're going to deal with multiple regressions later. They're much more complicated, but they're also usually often a lot more useful, and you can do a lot more with them. So with that, we're going to end. In the next lesson, I'm going to talk about how you interpret results from correlation and regression, how you deal with outliers, how you deal with curved relationships, and so going more in depth in this. And so with that, we'll end.